Great. Okay. My name is Solomon, and we are Professor Onime Clement here. Also, he and I will give you this Masterclass program, and so we will start with the high performance computing architecture for 20 minutes, and I will continue with the introduction to Parallel another 20 minutes, and I will also continue with the algorithms and concurrency, sorry. And we will have a tea break for 15 minutes. And after that, we will have Parallelizing serial to parallel OpenMP by Professor Onime and the HPC Demo. I hope you have already seen this prerequisite for hands-on workshop. If you have C programming knowledge might be really good, and if you have a command line, as most of you, if you are using this Linux, using command line might be a good idea. And if you already install for hands-on this code block C compiler, might be interesting. So if you have ever get a time, please try to install this software. So Professor Onime is from ICTP. He will introduce you to himself. So I will leave the floor for Professor so that he continue his first session. Thank you so much.
Okay, good morning, everyone. And thank you, Dr. Solomon. Let me see if I can get this screen sharing functioning. I hope you can all see my screen.
Perfect.
Okay. Good morning, and I want to thank Dr. Solomon and the organizers of this HPC Masterclass, series for the opportunity to be here today. My name's Clement Onime, and I'll be speaking to you about HPC architecture. This is just some boring profile about myself. I've actually been working with computers now for a pretty long time. Okay, but I do cover a lot of different areas. And I look forward to seeing many of you after this class being able to work or feel confident with HPC technology. Okay, so my style of teaching is, or my style of working is really quite interactive. So I would like you, the audience, to also provide me some input as we go along. So I usually have these slides in my presentation where I ask questions and I want to receive feedback from the participants. It's good to see that we're from many different nations, so it will be interesting to understand our views. Of course, I'm going to sort of limit our views and our experiences to science and as scientists. So the two key questions I want us to start with will be, why do we use computers? And then when we say we're talking generally as scientists. Why do you think scientists use computers? And then, of course, you are also an individual within the pool of scientists. So what do you, as an individual, use your computers for? I don't know if we can probably just take one or two quick responses. Are there any contributions? Okay, if not, we can simply just come back to this later. Okay, welcome, Professor Francesco. So science really has a well-tried and trusted approach, okay, to carrying out science in very many disciplines. This approach is simply used, and we basically start from observations on which we build theories, and then we carry out experiments to try and validate or disprove the theories that we have concluded. In certain fields, it's not that easy, okay, to observe things. Things like studying how the universe began is not very easy to be able to understand that by observation, because in contrast to the universe or even to the earth, we as human beings are not around for that long. So computing tends to be a very interesting vehicle for science. We can see that in the second portion of the slide here, we have sort of replaced the experimentation with computation, modeling, and simulation. Essentially, this is still complementary. Okay, so for many disciplines, you also do have experimentation going on, but you also have computation, modeling, and simulation. So this is a key way of approaching science now that is now globally acceptable. Sometimes some of the problems we have to deal with as scientists are really either too expensive to work on, or too difficult, or too dangerous or controversial. This slide just lists some of the areas where there are difficulties with carrying out experiments simply because of the associated costs, or because of the associated difficulties, or because it is dangerous for one's personal health or quite controversial. At this stage, it will have been good to see if some of us can provide some input as to the kind of scientific tasks we are performing with computers. I don't know if anyone is ready with the with any of these answers. And while we do have tasks, in many scientific disciplines, we also have challenges, global challenges that tend to be necessary, or that tend to be important to address to make to achieve new milestones as far as a particular discipline is concerned. So let's just now get on to defining high-performance computing. So high-performance computing, sometimes also called high-productivity computing, we shall ask ourselves the question about performance and productivity later on, is really about trying to exploit gains that we can obtain from optimizing computer hardware configurations and software for achieving faster results. Okay, one could say simply that it's really about size and speed. Okay, so we try to optimize our available computer resources to make gains in obtaining faster results, or even to address bigger problem domains, which is about the size. For science, using HPC properly ensures that we can get faster results, and we can also coordinate or function as part of large international groups of researchers, okay? Even carrying out research amongst nations, research that where the individual researchers are in different locations or different parts of the world. But this really requires us to know a bit about the computer hardware architecture, and also to have some knowledge of software programming. So I'm going to be focusing on this first requirement, which is understanding computer hardware with respect to HPC. Just before we get into the nitty-gritty of architecture, I just wanted to provide this slide just to encourage the young early career researchers amongst us that there's a lot of opportunities you can open for yourself when you acquire skills in high performance computing. For example, the airline industry requires a lot of logistics, so that there's a lot of planning and logistics that go on. And they use HPC to calculate even the scheduling of the various planes and flights and stuff like that. Equally interesting is the automobile industry. So car designs, even up to Formula One racing, even things like the wear and tear of the tires or the components in the Formula One cars are typically heavily analyzed using HPC. The semiconductor industry nowadays, to achieve many of the new processors that we have arriving on the market, tend to require HPC for design simulation and validation. Something that is not really too common is the fact that HPC is used a lot in the entertainment industry. So a lot of the animations, the movies, the big movies, and also the CGI effects we see nowadays tend to be carried out using HPC platforms. Healthcare is also quite possible to conduct research in designing new drugs, or even study ailments like cancer and tumor at a new level, all thanks to the power of HPC. There have also been industries like the food industry, where they employ HPC to design or to help in the design and optimization of shapes of containers, shapes of individual food items and stuff like that. So this provides a very interesting read. It doesn't require, on the right side of the slide, we do list various types of scientific disciplines, but they don't require you to be an expert in each of these disciplines to use HPC for the benefit of such a discipline. So by acquiring HPC skills, it doesn't matter whether you start from a computing background or a physics background, you could be of use, okay, and find yourself employment in any of these other areas, including banking and finance. Okay, let's get into the details of computer architecture. So the computer architecture, it all started, or the current architecture we have started in the 1945s with a gentleman who was called von Neumann. And he sort of defined or determined the main components we have in the computer today. Interestingly enough, this is the same design that we still use in many of our computers. He also spoke about changeable programs and how you can execute things sequentially. So he did a lot of the groundbreaking work. This is a block diagram of a microprocessor. The microprocessor is the heart of any computer, and it's made up internally of components such as the arithmetic logic unit, ALU, a program instruction decoder, a program instruction counter, as well as memory locations called registers. And all of these have interactions amongst themselves to give us the processing power that we have in the modern day computer. Of course, you'll agree with me that many of the computers we're used to, our laptops, our desktops, currently are in the range of terabytes when it comes to disk space. But our RAM is still in the area of gigabytes. But interestingly enough, there are supercomputers that exist already in the exabyte range. We shall build our way up to them to show how it has been possible. So our architecture is really looking at what was in the past, going up to what we have now, and all the way to how supercomputers operate. Many of us as scientists have already noticed that our laptops and desktops tend to be limited when we try to perform even large machine learning models. We have a lot of data and we try to train a machine learning model. We get a crash out of memory and funny errors happening all the time. These are related to the size and storage limitations that we have inherent in our computers. So the first part of what we'll focus on is understand the interactions between various parts of a computer, because by doing this, we can actually design better software and even format our data to improve performance. In the beginning, let's say not too far ago, there was a processor. Well, this wasn't really the beginning, but somewhere around the 90s, we had a processor called the Pentium 1, which was quite speedy. And it was revolutionary because it was the first processor to include memory internally. So prior to that time, most of the memory in a processor were really the registers. But the Pentium 1 introduced additional memory, which was used specifically for caching. Okay. So we see that in the Pentium 2 processors, they just appears that the cache was made a little bit bigger. The same with Pentium 3. Okay, so the ratio between the cache and the processor itself appeared to have dramatically increased. Coming to the Pentium 4, we see that the cache now appears to be bigger than the processor itself. We nowadays talk about multi-core processors. We are no longer in the era of single-core processors like the Pentiums were, but even then, the trend has also continued. So the cache also is part of a modern processor. So whether we have 6 cores or 4 cores or so on and so forth, there's always going to be a significant portion of the silicon chip that is devoted to caching. Can the cache slow down performance instead of improving it? One is inclined to say yes. You find that there's always an overhead. Okay, mathematically we can determine that there's a latency, okay, between the data arriving to the processor and the data arriving first to the cache. It introduces an additional latency in the processing. And if this isn't well managed, it can reduce the performance of an application rather than improving it. Over the years, there have been various attempts at developing algorithms, okay, to try and help the caching or help in the decision-making of what to cache and what not to cache, especially as the cache is not really as big as our regular RAM, okay? So we have started with the era of one computer and one processor. These tend to be quite limited in their abilities. It's getting to be almost impossible to even increase the size of memory in a laptop computer once you've bought it. Many times they are no longer openable. You simply just have to stay with what you bought. And then there's also technological differences. So if you have a hard disk as opposed to an SSD, there's always size and speed performance. One challenge or one challenge that processors face has always been the fact that since they have limited memory inside, they need to get data from an external part, okay, or from somewhere that is outside the processor. For example, inside a microprocessor, we tend to have registers and we tend to have cache. Here we just have some information about the relative speed of the processor getting data from the register as opposed to getting data from the cache. We see that that's already 10 times. And then if it has to go to RAM, okay, then we're looking at a 5-fold increment in the speed. Then if it's an internal hard disk, this is also an order of magnitude slower than even RAM. Before we talk about external devices like external hard disks and so on and so forth. So accessing data, or if our software application needs to access data that is on an external drive, okay, for calculations, it's going to be way slower than if that data is available from the internal disk, or if that data is available from the cache that is within the processor. Of course, the sizes of these memory locations tend to be increasing in capacity as we travel down the hierarchy. So the registers are just a few kilobytes. The cache tends to be megabytes. RAM, we're talking of gigabytes. Disks, we are now looking at terabytes. External devices, we are talking of multiple terabytes. Okay, so how do we improve performance of single processor, given the fact that we have these challenges of latency with memory and sizes? The key approach has been to sort of use multiple processors together to solve a given task. We are going to try and focus now on just the memory aspects of things. So when we talk about multiple processors, many computers are designed in such a way that all the processors or all the cores can access all memory. So for example, if you have a laptop that has 4 cores, the hardware of the computer typically allows all the core to be able to access the 32 gigabytes of RAM or the 8 gigabytes of RAM you have in the computer. And over the years, there have been 2 approaches to how these processors access memory. The first is the uniform memory access, called the UMA, and then the non-uniform memory access, called NUMA. So this is a graphical representation of how the arrangement goes. So in a UMA computer, we tend to have all the processors having equal distance to the memory. Okay, so the distance from any of the cores or any of the processors is always the same in accessing the memory. And this is really an inefficient design because you can quickly starve the other processors. As long as one processor hogs the entire part, all the others have to wait. They just have to wait. It's a kind of a single line telephone. Every other person is on hold as long as these 2 are talking. The NUMA tried to solve that by saying, okay, let's partition the memory according to the number of processors we have in the computer, and then we have a fast interconnection between the processors. So each processor gets a portion of the memory, but it can access the memory attached to other processors. And there is a finite distance, okay, to other memory, as well as very fast or short distance to the memory directly attached in a NUMA architecture. Needless to say, all the ideas about caching required some updates to be able to deal with multiple processors and multiple cores. We've had various new aspects of technology coming up in computing, which speaks about cache coherency, or even multi-queuing and hyper-threading. I think you may have heard these buzzwords one time or the other. So when we have a single shared memory, it's very good from a programming perspective. Okay, there's only one address space our program needs to look at. We can put data in that memory, we can do things with it. And then different tasks can actually share this data without great difficulty. There's a need for coherency, especially when things are changing. And then when we have caching, there's also the fear that sometimes you may cause what is known as cache trashing, where the cache is just rapidly changing and doesn't give any significant benefit to the application. And this tends to degrade when we have more processors. So the more CPUs we have trying to use either a cache or a given memory area, the more challenging it becomes to try and maintain consistency. In the shared memory model, a programmer is really responsible for synchronizing everything. I believe if we dwell deep enough, we'll discover that many of our laptops and desktops today are no longer single processor. If you have an i3, you have a multi-core device. So you have multiple processors. Okay. And then we may have also noticed that it doesn't seem like going multi-core really gave us the improvements in speed that we would have expected. And this is really because we cannot take advantage of the multi-core without redesigning many software applications. Okay, so in summary, we have looked at single computer evolution. We've seen that microprocessors can be improved by increasing the speed. Okay, we can also have these microprocessors work smarter through the fact that they have internal cache. And there have been interesting techniques and algorithms like pipelining and prefetching, okay, that have tried to improve the way processors work smarter. There's also working in parallel. So nowadays we're talking about multi-core and hyper-threading. And we have also briefly examined how computer hardware has improved, going from UMA to NUMA, and also things like the management of communication or memory channels so that we can get speed benefits. All of this has been from the single processor era. I want to show an example of a very recent processor. This is in the processor that was used in one of the supercomputers. Okay, and it boasts about 48 computing cores. Okay, but we shall talk about this in a little while. I think somebody raised their hand. Bemut Zenebe. Dr. Solomon, do we have time to take questions interactively, or we should wait till the end?
No, yes, please, you can take any questions. Who raised? I haven't seen that. Okay, let me check that.
Okay, I thought
somebody... you can ask. It was an accident. Yeah, it said it was an accident. So it wasn't a question.
Okay. Okay, so I just reviewed the chat to see that we didn't have anything outstanding. I know I'm going a bit fast, but I'm trying to sort of make time. We have a lot to cover in a short while. Interestingly enough, there are, let's say, whole courses devoted to some of the concepts I'm sharing today. Okay, another recent development in computing has not just been multi-cores, but also many cores, okay? And the many core idea is based on something called single instruction, multiple data, SIMD style of computing. And it's been implemented in form of a device known as an accelerator. So it's typically a computing device that has its own RAM and can run what are known as threads. Threads are a bit like lightweight processes, okay? And they are very efficient because they are not as heavy as running a regular process on a CPU. There are two notable examples. One is the NVIDIA Tesla GPUs. We may have heard of this. And there used to be also the Intel Xeon Phi boards. I think these are more or less going out of fashion. But you can see that rather than talking of tens of cores, we're talking thousands of cores. So for the NVIDIA, this NVIDIA device is already, I guess, maybe 5 years ago. But then we see that it had about 2,000, almost 3,000 cores. And it can deliver the same or better computational power than a single multi-core processor. Okay, it ran at a lower speed, okay, but it did have also a lower power consumption compared to trying to build a computer with this many cores. So this is the same for the Intel. The ideas are similar, but the approach to programming were different. Okay, so we shall just explore a bit of the NVIDIA one and leave the Intel one for later. To use an accelerator, you do need to have a host computer. Okay, and you do need to have a host computer, and it's always a device that sits inside a computer. So you must have a host computer to use an accelerator board. It really cannot work by itself without a host computer. The internal memory in an accelerator, it's also similar structure to that of a microprocessor. So we have internal registers, okay? It's typically based on the internal hardware. Then it has some RAM. Okay, so we can see here that this has 12 gigabytes of RAM, but the host computer could have 64 gigabytes of RAM. Okay. The operating frequency is 915 megahertz. The host is running at 2.4 gigahertz. But then even with the slower speed, an accelerator is still able to outperform a regular processor. So the RAM in the accelerator is divided into 3 areas for programming. There's always local memory, which is private to a single thread. There's shared memory, which is private to a block or a group of threads. And then there's global memory, which is available to all the threads that are available on the device. Programming an accelerator of the NVIDIA type tends to require moving data back and forth between memory. So you load the data into the memory of the host, and then you copy from the RAM of the host into the RAM of your accelerator. Okay, then you perform computation on the accelerator board. Okay, and then when you get the results, you copy the results out. Okay, so there is always a speed difference. So you can see that for the lower part of this diagram is the accelerator, while the upper part is the host computer. So we have the 64 gigabytes of RAM and the 20 cores, okay, as shown here. They typically obtain about 30 to 40 gigabytes of speed between the host and its RAM, whereas within the accelerator card, we can see that the speed performance is really quite significantly better. Okay, but the speed interactions between moving data to this memory is always slower. So it does require us to structure our applications, our software, and our data manipulations in a way that can take benefits of the device that we have. This has been more or less one of the challenges associated with HPC. Okay, so let's move now to HPC clusters. The cluster concept is typified with this diagram, okay, where we have a set of small fishes. Each of them are really tiny looking when compared to these bigger fishes, which are, one will say sharks, okay. But as you can see here, the smaller fishes have coordinated themselves into an attack formation. And that formation looks like it's capable of swallowing and taking out the shark. Okay, so the key concept with respect to clusters has been we can obtain high performance, not just from tuning the hardware of a computer, but by grouping computers together. So the computer clusters tend to require more than one computer, okay? Then you also need a network, okay, to link these computers together. There has to be some linkage mechanism amongst them, especially as there's a software layer that is typically referred to as the middleware that coordinates the activities and the tasks that are going to happen on all these computers. The net effect is that a cluster looks like one big computer, okay, one big object, and it can take on tasks that would not be possible even with a single large computing device. For the network technology, there have been proprietary links developed over the years, and most of these you can find with Cray supercomputers. But we do have some open technologies like the InfiniBand or even gigabits. Okay, nowadays we're already talking about 100 gigabit Ethernet. Okay, but then the InfiniBand technology are way better than that. Traditionally, we used to have two brands, okay, for InfiniBand, but it looks like there's now more or less just one company that is dealing with InfiniBand technology. Incidentally, if I remember correctly, that company was also bought over, I think that's Mellanox, and that was bought over by NVIDIA, if I'm not mistaken. So the landscape is getting a bit tighter, as in we're looking at monopolies. Anyhow, regardless of the interconnections that are linking the computers together, there are several different strategies. There's the shared bus, okay, where all the computers use a common facility for communication. There's also a link or line topology. There's a two-dimensional mesh. There's also the fully connected or hypercube, and sometimes you hear buzzwords like torus interconnect and stuff like that. Those are all basically trying to describe how we coordinate the interconnections. So in these diagrams, each of these circles is a node or a full-fledged computer. So we see here that each one has connections to 3 other or 4 other computers, and so on and so forth. There are various reasons why this is done. Okay, so we can see also even effects about bandwidth, okay, and latency that appears on these links. Physically, a cluster of computers could look something like this. So there are several computers that are performing calculations or computations on behalf of the users, and those tend to be called compute nodes. These may be connected to a high-speed switch, the InfiniBand switch. They also have probably a gigabit switch for regular traffic, and also maybe storage. So the storage is probably always kept apart. then you have a coordinating computer that sort of coordinates all the activities that are happening here. And you sometimes have a specific computer for logging. And many of us who have used supercomputers, such as the CHPC in South Africa, would appreciate this architecture because most of the time your connections come to the login node, and this is where you submit your jobs. And then it gets scheduled by the master node and eventually run by one of the compute nodes, okay, using some InfiniBand switch. Logically, software applications on a cluster tend to see this. You have your parallel applications that use parallel programming environments, and these can use multiple computers at the same time. But each computer on its own is also able to run sequential or serial applications, and all the computers are connected by a high-speed switch. Okay.
Can you switch off your, can you mute?
So when dealing with clusters, we tend to look at two types of architecture. There's a distributed memory architecture, and then there's the hybrids that are becoming quite popular. If you remember, we spoke about shared memory architecture when we were considering multi-core computers. So that's from the everything. So shared memory tends to happen inside one computer, while distributed memory is concerned with trying to coordinate memory across several physically separate computers. For example, if we look at this diagram, we can see that this block here represents one single computer. So this is a cluster where there are 8 physical computers connected together. So each of these computers has its own memory processor with a cache, and also input and output subsystems, and even network connectivity. And each of these can run shared memory application on its own, okay? And then the distributed memory architecture is now about connecting the RAMs that are available in each of these computers to create one big, massive pool of RAM. So even if the physical limitation of this computer was just 64 gigabytes of RAM, if I have 8 of them, I'm already talking about 512 gigabytes of RAM. Yes, thereabouts, yes. Okay, as my total aggregate availability from the cluster. So this means I can run bigger programs, or even attempt to do training of bigger jobs if I understand how to use distributed memory. I can overcome the limits of a single individual computer. So for distributed memories, we tend to scale the memory with the number of processors, okay? There's little interference, so there's not a lot of overhead with coherency, especially if we structure the application very well. But then it requires good know-how in programming to be able to use it effectively. What is more common across clusters nowadays is that you can have softwares that perform both shared memory and distributed memory. So they can also do some shared memory application, exchange variables within a single computer, and at the same time use the memory of another computer for tackling bigger jobs and things like that. So the advantages are really the same advantages we've come across in previous slides. And they are easy to build using simple components. You don't need to have a dedicated hardware or a special company to build you a distributed shared memory cluster, or even a distributed shared memory supercomputer. Okay. So when we introduce accelerators into the mix, we tend to have a fully hybrid system. So it's no longer just distributed plus shared memory, but we now have acceleration also happening within each computer block as well. So it makes the computational power drastically way bigger when we have this kind of clusters. For certain applications, especially those that deal with vectors, you tend to have speed ups of up to 100 times. Okay, but then you do require some additional effort in programming the accelerators to get this advantage. But the interesting thing is when you get it done, you can enjoy a very significant speed up. So clusters are really fundamental for HPC simply because they are easy to upgrade. We don't run into the situation where we cannot upgrade the RAM like we found with our single computers. But as we increase the number of nodes in the cluster, we are increasing the capabilities of the cluster. Just to mention, some of us may have heard of grid technology. So grid computing and cloud computing are two paradigms that have also been used, I will say, in the last 20 years. Okay, they've gained a lot of ground in the last 20 years. Grids were more or less trying to look at interconnecting clusters together so that we can have clusters that span different geographic locations. It was modeled after the electrical power grid, hence the name grid computing. But then everybody is using clouds now, but many of the concepts in cloud computing actually came from HPC and clusters. Okay, so just to summarize, HPC can actually be used on different hardwares. Interestingly enough, we can apply the concepts of HPC even to our modern cell phones. So it's possible to build a cluster of cell phones and even derive computing power from this. I do have, okay, maybe not cell phones, but I do have colleagues that work on the field of IoT. And some of the current buzzwords they are talking about is doing machine learning on IoT devices, which are supposed to be tiny devices, even with many with less amount of memory compared to cell phones. So this concept sort of shows that you can do HPC even on mobile devices or even single computers. It doesn't matter whether you have desktop computers. If you put them together in a cluster, you can get the power of a bigger and a larger computer that will have cost thousands of dollars. Of course, grid computing and cloud computing are also enjoying the benefits of HPC. One thing I should say is that all modern supercomputers are really just using or built on using the HPC concept. Before we move on to supercomputers, I just wanted to talk about some of the challenges, okay, that we face in the field of HPC. One is really there are new processors coming out all the time. So almost every year you are sure that there's going to be new processors because there's a lot of competition. So you have processors from Intel, processors from AMD, and processors from ARM as well. The communications hardware, things like our network, are always slower than what's happening on the processor level. And software is really just trying to play catch up all the time. So software is sometimes generation behind, okay, with the available processors. When we talk about existing software, there's also challenges with trying to come up with new algorithms or even rewrite existing algorithms so that we can exploit HPC architectures. Especially because it seems to be that we need specialized training, okay? We need to improve our programming skills. There's also limited know-how. So many times when a new processor arrives, you need to study it in depth to be able to understand how things are done. And even development tools like compilers and so on and so forth are still playing catch up to processors. So this is challenging. I will briefly end now with examples, a couple of examples of recent supercomputers, especially those that are at the exascale level. So this was a computer that was #1 in the world, I think about 5 years ago, and it was located in China. Okay, it had regular Intel cores. It had GPUs or accelerators, and it had also proprietary CPUs all as part of it. It offered a global total of 206 terabytes, and they also had their proprietary interconnection, but it delivered a whopping high amount of computational power. So it was #1 on the top 500 list just a few years ago. But things have turned. Even currently, this was also a machine that was, I think, on #1 maybe a couple of years ago. Okay, and it was built using the A64FX processors I showed earlier, which was completely custom. So it didn't use Intel processors, but it had about 7.3 million cores, okay, in that supercomputer. And over 150,000 computer nodes were connected together to deliver almost almost 500 petaflops of performance speed. And this was #1 in June 2020, but this has already been superseded by another machine that I believe was installed in the US either last year or the year before. Okay, so you can see the rapid evolvement of technology. Even a supercomputer with 150,000 nodes is no longer considered the fastest in the world, despite having over 7 million cores. It's not the fastest anymore. Anyhow, if you look at the top 500 computers.org, there are some trends that I think is good for us to keep in mind, especially with respect to technology. One is the fact that all supercomputers nowadays use Linux, as at least the top 500 supercomputers in the world use Linux or some form of Linux as their operating system. And then the main way that the supercomputers are achieved is almost exclusively using clusters and HPCs like we have talked about today. And so I will just want to encourage you in concluding that HPC is something everyone can get into. It will allow you to tackle bigger scientific problems, obtain faster results, even if you have not so fast hardware, not so great hardware. There are techniques we have briefly mentioned today, just things like cache management, the memory architectures, the interconnection, and of course, parallel computing, which we shall do a bit of later on. So I want to thank you, and I don't know if we have some time for questions.
Yeah. Thank you, Clement. I think you can answer the questions soon. I mean, there is a few questions. Have you seen them? It is When it comes to processors or architecture, what are the AVX, SIMD, and SSE? That's one of the questions I have seen.
Come again, please. Could you repeat the question?
When it comes to processors or architectures, what are AVX, SIMD, or SSE?
Okay, SIMD is a concept known as single instruction, multiple data. There are various ways that computers treat data, okay? And the single instruction, multiple data is a style of parallelism that allows one instruction to act on multiple data. For example, in the field of engineering, it's sometimes common to work with vectors. Okay, and when you are working with vectors, you want to multiply maybe a vector by an integer. Okay, and this requires your vector is sort of like an array of several integers or several numbers connected together. So carrying out a multiplication. Okay, and so you have a situation where the multiplication of a vector with an integer requires you to perform that multiplication over the various fields of the vector. So if you are using a normal computer, you will need to write a loop, and then it performs the loop one by one. So, but with SIMD kind of processors that we see in many core, you simply load your vector into the memory and you issue just one instruction. You don't need to loop. Okay, so one instruction will be applied to all the locations of your vector at the same time. So you carry out your computation at a fraction of the time that it requires. It's because you don't have to loop. And this tends to be very useful. SIMD's type of computing tends to be useful when you have vector or matrices to deal with. Okay, so for those kind of computations, SIMDs will sort of always outrun a normal processor regardless of the speed difference. AVX and SSEs are extensions that were added to the regular CPUs to try and help their performance, okay, with respect to vectors. They still require some looping, but they are extensions that are built into, or hardware optimizations that have been built into microprocessors to try and help with carrying out vector computations or similar computations, handling special data types on your normal CPU. I hope you get me. So where you might see SIMDs on many cores, AVX and SSEs tend to be on the single core or multi-core processors.
Okay, but there is another questions, but I think since we don't have that much time, probably if we got time, we will go back again for the questions. And I think it is better to continue to the next presentation. Thank you, Clement.
Thank you, Dr. Solomon.
Okay, let me show you. Can you see my screen? Okay, yeah, okay, Professor Clement already showed you the hardware part, which all the architectures, and then what is really some of the bottlenecks or something. And at the same time, even if you have a hardware nowadays, you have to also to consider the software part. So I will try to be as fast as possible because there is a lot of things we would like to show you. And I will try to be as fast as possible to show you this introduction to Parallel. So before we discuss about parallel, we have to discuss about the serial. As you know, the traditional software which we develop nowadays and which we write is a serial. Every instructions will be written and all instruction will be try to execute line by line. That is what, most of the time, even if you have some kinds of conditions like if clause or what else or whatever, any while, all the instructions will be performed line by line, every instruction. So that is a traditional way we have been using. So every time when you try to write a software, what you do is that you have to break all the problems into a discrete series of instructions. Then you try to implement that. So instructions are executed sequentially one by line, and all that sequence of line will be sent to the single processor, and that processor will, it might take one CPU clock or any time which is dedicated by that CPU performance. So that is happening. But as you can see, assume that if I have a problem, I have to break it into section until n, until I finish all the problem, and then each process will be fed into that. So this example, let me give you, if I am working on a payroll, and if I have a 10,000 employees, and what we do is that we have to do for each employees every tax, provident fund, everything, whatever you do in any calculations to do a payroll and to have the net value, you have to do some kinds of calculations. So for each employees, you have to provide for that single processor, and it might take, assume that if it is taking one CPU clock for one employee, that means it will take you 10,000 CPU clock for 10,000 employees. So this is the way where the traditional software execution works in a serial. So what is parallel means? It's just simply multiple computer resources, because Professor Clement showed you that you can have many cores nowadays and many high-performance machines. And what you do is that you just want to use that resources, that multiple compute resources to solve a problem. Okay, so you have a discrete parts that can concurrently, you should have to do this parallelly. Unless if you have some kinds of problem which they have to do sequential, you have to follow the same sequential procedure what you have been doing. But if the problems are broken, and then if they can be performed parallelly or concurrently, then you can create this parallel computing software program, and then you can do it using that. However, if you want to do that, you need some kinds of control, and coordination is really, really important. So in this presentation, we will try to see how we can coordinate, and then how we can control, and then try to collect different results from one specific for one problem, and then do a parallel. So the same kinds of examples which you have already seen. For example, if I have 4 processors, and if the problem can be decomposed or broken into 4 parts, then I can break it into 4 parts, and then two of them can be parallel. So it minimizes 1/4. I can finish 1/4 of the time for the problem, which we have already seen it previously. So just to come with the employment example, the payroll example, if we have a 10,000, if we have 4 processors, then we can do each employee separately. We can do it parallel. It can be broken, and then it can be discrete, and then it can be done concurrently. So I can do from employee 1 to employee 4 or to employee n, and then all of them can be performed. Assume that if I have a 10,000 processor, that means I can finish this employment payroll task within 1 CPU clock. So depending on the kinds of processor you have, that determines the time. So you can minimize by using the parallel rather than using the serial, which we have been doing traditionally. So what is parallel computing? It can be broken into a discrete piece of work, and then it can be executing a multiple programming instruction. And then it can be solved by less time. That is the most important thing. So, well, as Professor Clement shows you, one computer can have a multiple processor, or you can use that one single computer, or as you have seen a cluster, you can have many computers connected with the network, can perform any tasks in a parallel. So as long as you have any multiple resources, whether it is a single computer or computers which are already interconnected with the network, it works. Both of them can solve the problem with use for your parallel. Yeah, so this is the things which most of the things which Dr. Clement already showed you. I will pass because he has already shown you all these different networks. Let me come to why we use a parallel computing. Well, the normal now, the real world problems are already parallel. Every events are happening together at the same time, even interlinked together. The same problem can be parallel. So if you want to model or simulate or understand any real world phenomena, then you have to have some kinds of parallel understanding. So in any field, which Dr. Clement already showed you, that if you want to model that, simulate or understand any complex problem, then that is parallel computing. So we need to express this world, particularly for our team in AI, whatever you do or mimic any kinds of human being or neural network, what you do is that you need a parallel computing. So these are some examples which Clement has already mentioned. All the real world is the same kinds of, it is done, if you want to model, then you need a parallel programming. So the reason is because it saves the time, because it saves money, because you are utilizing your resources efficiently. And sometimes even nowadays, you have a better smart mobile phone or even a desktop with CoRE-AI 3 or AI 7. Most of the programs which are executed in that specific device are, it is serial. And that means we are not efficiently utilizing our resources, which we have already had in our hand. Even most of the time, for example, in any institutions in the universities, there are many computers which are already interconnected with the internet, but with the network, that then they are not using, we are not using it. Most of them are sitting idle, and we are not using the resources properly or optimized format. So as you can see, if we are working together, in Amharic, it is called, if you are building a house together, it is called Demo. That means we work together. So if you work together, you can minimize the time and your effort. You can finish with the small amounts of time and saving money. So as you can see, there is many large and more complex problem that can be also solved by parallel programming. For example, I am in natural language processing, which I work a lot. And through that, for example, or image processing, sometimes, human beings, you cannot program image processing through rule-based or some kinds of statistical-based. Rather, you can have such complex problem by using other kinds of methodology or algorithm, and that can be implemented efficiently using this parallel programming. Clement also mentioned about the entertainment industry nowadays. They are using lots of this animation that has been done is through the parallel high performance machine computing, and then that helps them a lot to create, innovate new ideas which we can't even imagine before. So it already changed a lot of ways of thinking, way of doing many things. And then even for Galaxy or, you cannot see it graphically or simulate it without this high performance machine. So with this parallel programming, all this can be managed. So we need a concurrency. That's one of the things which we think before we go to the programming part. We have to think that concurrency is the most important. Single computer resource can only do the things at a time, or multiple computing resources can do many things. As you can see, it can also work in a social networking, in e-commerce, economics, all the things what we need to do nowadays. Also, it's a part of parallel computing. Okay, I will pass all the things which Clement already covered. So for science and engineering, like these many simulations for industry and commercial nowadays, in financial and economics, oil, web search engine, most of the things in bioinformatics. Okay, Clement showed you this Van Neumann architecture, which is already a groundbreaking, and most of the rules which we use now comes from Van Neumann. And the reason why I mention now is I just want to show you this Flynn's classic taxonomy, which is already mentioned a little bit about this instruction stream and data stream already exists, and every process we thought should have to be included in this instruction stream or data stream, or with the 2 dimension of possible states, single or multiple. So we will have single instruction, single data stream, single instruction, multiple data, multiple instruction, single data, multiple instruction, and multiple data. I just want to try to show you how this means. So a single instruction, a single data means the serial which we have already been doing, this traditional. That means it is deterministic. It's all type of computer. That means you have an instruction of pool, and one instructions will be fetched, and one data will be fetched from the data pool, and that will be executed in the processing unit. That is a single instruction and single data. So the programming, like you can load A, it's just a set of instructions, load B, and compute A plus B, store it in C, compute B, multiply by 2, store it A, or something just like that. Such kinds of instructions which we have been using is called single instruction and single data. The second one is single instruction, multiple data. Is you have a single instruction which will be computed for each on each different data that can be executed, and like vector pipelines or process arrays can be implemented. So let me show you examples. For example, you have an instruction pool, as you see on the right side, and you have a data pool, and different data will be fetched, and only one single instruction will be fetched, and that instruction will be executed in different processing units, but with different datas. For example, if you are adding arrays, just to show you an example, just adding the i's, every element will be added. So as you can see, x0, y0 plus x1 plus y1, x2 plus y2, x3 plus and y3, and so on and so forth. So it can be done parallelly, and then it is the summation is an instruction, but all are this instruction will be computed in different data. So such kinds of examples, if you have, it is called single instruction and multiple data. Just to show you how do we do it, especially in a condition, this single instruction, multiple data. As you can see in the above, there is if B equals to 0, C equals to will be assigned to A, A will be assigned to C, or else it will be A divided by B will be assigned to C. So these are the first examples you have. For example, A is 5, B0, C0 in processor 0, A4, B2, C0 in processor 1, A1, B1, and C0 in processor 2, A0, B0, and C0 in processor 3. So now we can compute like if B equals to 0, so B0 is in processor 0 and in processor 4. So this will be computed and C will be, A will be assigned to C. So 5 will be assigned to C and 0, it is already, but will be assigned to C. But this will be idle because it doesn't fulfill this requirement or criteria of condition. So what will happen is the processor A and processor 3 will execute and processor 1 and processor 2 will be idle for that time. For the second one, then processor 0 and processor 3 will be idle because it fulfilled the else condition. Then A divided by B will be assigned to, so 4 divided by 2 will be 2 for C, and 1 divided by 1 is still, it will be 1 will be assigned. So such kinds of things, even if you have a serial instructions in parallel, can be executed differently. Multiple instructions, single data means you have a different instructions from the instruction pool, and only single data will be fetched from the data pool, and this will be executed like this. As you can see, there is different instructions, but the single data. And you, as you see in processor 1, the instruction will be A1 multiplied by 1. In processor 2, A1 multiplied by 4. And in PN, mat n equals to assigning to A1. So you have different instructions will be implemented in a specific single data. It is called the last one is called multiple instruction, multiple data. That means you have lots of instructions and lots of data which you can execute. It can be synchronized or asynchronized according to the problem, or deterministic or non-deterministic. Like you can see, there is a lot of instructions from the instruction pool, and there is a data pool. All will be executed in different, so multiple instructions or multiple data. So all your problems might fall in this Flynn's taxonomy, and then you might think which one is really fit to your problem. Yeah. So now let me come to the programming part. Well, if you want to parallelize any serial, you can do it either automatically or manually. Okay, there is many softwares which are already developed, trying to work automatically and then try to identify which set of instruction can be done in parallel, and then try to do it. So, but if you are doing it manually, it will be complex, error prone, and then sometimes you can iterate if you have to do it again and again, looking at it. And then probably it might be a better one rather than using the automatic one, because if you do it in an automatic, they do only the loop or some other specific parts of your code will be executed, or trying to do the parallelize, but they don't look all the kinds of things that are really can be parallelized. Yeah, so if it is automatically, most of the time they do check only the loops of the iterations, and often then it is in different kinds of stage. Okay, I pass the questions, and yeah, and so yeah, if you are doing it yourself, probably if we have time, we will have a demo using OpenMP, how you can try to change the serial code to parallel. And this is a complex. Yeah. Okay. So two concerns. For example, if you are parallelizing and then using different resources, Clement already mentioned you might share if you are using like NUMA data might be stored in other parts of the CPU, and then you have to bring it from others. So you parallelizing compiler will move around to uncover parallel operations, data localities. That's what I was trying to discuss. And then you have to get it data from another processor. So you might increase the time if you are trying to do. So probably what you have to do is that at least you have to assign the same kinds of tasks that will be done in one specific data together in one processor, and then try to separate this way, unless otherwise you are creating additional latency to your system. So if you want to do this, you have to at least understand exactly the concept of dependency. Dependency means the exists between programs statements when order of statements execution affects the result of the program. For example, if you assign a task for processor 0, and if you assign another task for processor 1, if processor 1 is waiting until processor 0 finishes its task and then deliver a data, then that means processor 1 is dependent on processor 0. So dependency means that. Data dependency means just multiple use of the same locations in storage by different tasks. So dependencies are really important to parallel programming. So if there is a dependent between different tasks, then you have to understand exactly you cannot parallelize that, or you have to adjust your scheduling system to fit different workers. The same kinds of time can be done in different tasks, and when you assign it. So that means you have to see the inhibitors of these dependencies. So let me show you an example before we carry it out. So I'm not asking you a question. So for example, this line of code, do J from starting to the end. So for AJ equals to AJ minus 1 multiply by 2. So that means in order to multiply AJ, A of J, and it expects the results of AJ minus 1. That means it has got a dependency. In order to do the process of this work task AJ, you need AJ minus 1 to be performed. So that means you have a data dependency before you compute AJ. So such kinds of things cannot be parallelized in this situation. So you have to schedule your system how it works. So parallelism is inhibited in this situation. That was I was trying to discuss. So there is different kinds of dependency already exists. It is called flow dependency. Flow dependency means a read after a write. A true dependency, read a value after it has been written into a variable. So you cannot, you have to write, read value after it has been written. So you have to read any value after it is written in that specific variable. So such kinds of things, it's called flow dependency. I will show you some examples. And the second one is called anti-dependency, write after read. Write a new value into a variable after the old value has been read. So you have to wait until the old value already read, and then you can read you can take that specific information, because that value must be read before you execute some kinds of task into that specific data. The third one is called output dependency, write after a write. Write a new value into a variable, and then later on write another value into the same variable. So there is these three: flow dependency, anti-dependency, and output dependency exists. Let me show you with examples. Now this line of code, A equals to 19, B equals to A, C equals to A plus D, A equals to 5. Just want you to remind you this flow dependency, read after write. let's check read after write. So which one is from which is read after write can be done? Who can give me example from this line of code? Okay, read after it is from 2 to 3. I mean, you know, A must be read. Sorry, read after it is written. So A can be read after A is written, and A also can be read after A is written. So this flow dependency will be between 1 and 2 and 1 and 3. The second one, anti-dependency, right after it is read. Right after it is read. So between 2 and 4 and 3 and 4, that means you can write a new value 5 after it is read by B and by the second line of code and by the third line of code. So here the an anti-dependency between B 2 and 4 and C and 4. The last one, output dependency, right after write. Okay, so right after write means A must be written first, and then you write A equals to 5 after this one is written. So right after write will be between task 1, instruction 1, and instruction 4. So you have to consider all these dependencies before you continue to make parallel of your programming. Okay, now as you can see, this is an array summation between two arrays B and C, and you can AI. You put the result in AI, and then you assign in the same loop DI into AI. So this can be, is there any dependency or can it be parallelized? These things can be, yes, because there is no any dependency, because AI can perform in different data and it can assign different data, and the next loop will be done separately. So each iteration can be done parallelly. There is no dependency in it. However, what about this one? But this one, as you can see, even if we have the same thing, except this AI plus 1 will be assigned to DI. So there is a dependency between each iteration. So we cannot do parallel the way we have already shown you previously. In this, another example, I just want to show you BI, CI, but it will be stored in A of X of I. And we don't know the X value. So you cannot determine in such situation. Xi is unique. We cannot exactly know the X value. And then because of that reason, then we cannot understand exactly. You cannot understand exactly. There is no idea between the relationship of these different iterations. We know between the two previous examples, but in these conditions, you might not know. So you might have such kinds of examples. So you have to consider all these conditions. So how to handle data dependency? You know, you might have distributed memory architecture, communication required, or synchronization, any synchronization point. Probably you might have a shared memory architecture, read and write operations between tasks. So these tasks must be done. So there is many examples, execute read, execute write, concurrent read, execute write, exclusive read, concurrent read, and concurrent write. I'm not, because there is no time, I cannot explain all these things for you, but what does concurrent write mean? That means write only if all values are identical. arbitrary, write the data from a randomly selected processor, you can do it, or prioritize, follow a predetermined priority order, or sum, write the sum of all the data items. So this way you can do the concurrent. Concurrent means parallel. Okay, so Clement mentioned about cache coherency, because if you are sharing a memory, then the cache should have to have the recent values. And how do you manage this cache coherence in a multiple system, particularly if you have a different memory, NUMA, or even if it is shared memory, UMA, then how do you guarantee? So you need some kinds of coordination. So I just want to show you one example. It is called invalidates the memory. For example, in the first, as you can see, processor 0 had x equals to 1. Processor 1 has load x equals to 1, and the memory is x equals to 1. However, processor 0 changed the value x to 3. So whenever processor 0 finishes, then it should have to be invalidated in the memory, and then also invalidated in the other processes which already exists in that high performance computing architecture. So this is the first one. Or the second step, what you do is whenever a process changes the value, automatically update the memory into the shared memory, and then at the same time send that specific updated value to the processor. So there might be invalid protocol, update protocol, depending on your system which you are trying to use, update and invalidated. This is the things which I have already discussed in this slide. So each value of each data associated with any state, whenever you change any values, it should have to be changed, invalid or updated into the system. So this is the way the protocol that I have been already telling you is either in a shared state or in a dirty state. Dirty means that the value is already changed or is not the correct one. So invalid means you invalidated it. Sometimes you might flash if it is a dirty one and then write the new one, and then you might read the shared one, the new one. So these are the architecture. I'm not going through it since we don't have that much time. But let me show you an example with processor 0 and the processor 1. And this is the third row column is for processor 0 memory, and the fourth column is for processor memory, and this is a global memory. This is a cache also. So for example, you have a value of x equals to 5 and y equals to 12 at the beginning. So whenever any memory read, for example, processor 0 read x value is 5, it is shared now, it is changed. And in the memory, it says it is shared. Now the second step is processor 1 read y equals to 12. It is shown the state shared, and y equals to 12 is shared. Now the third step, x equals to x plus 1. So x, processor 0 changed the value, modified it by adding 1. So x becomes 1. So at this moment, the state changes to dirty. So in a memory, it becomes x equals to invalidate. Okay? So in the memory, in the shared memory, it is invalidate, but in the processor, because it changes, it is dirty. Now, the same kinds of y added number 1 into the value of y, it becomes y equals 30. It is dirty. The same thing in the shared memory, it is invalidate. Now, if it is sharing to the shared memory, what will happen is y equals to shared to the global memory. Now the state changes, and at the same time, also it is changed the state. The same thing for every value. If it is changing, then it will change because it is shared. So this way it continues like that. So this is the protocol which you have already seen. So in a parallel, this coherency is executed by different protocols as I was showing you. So you can do it parallelly in a program using different protocols. Well, there is also a Snoopy hardware which is already installed to perform such kinds of processes into the system. It is called Snoopy cache. Each processor has a cache and tags for each, and there is a main memory. And every time this dirty will be, whenever someone changes a value, whenever any processor changes a value, then it shows automatically this Snoopy hardware catches that specific and then try to manage this cache coherence system using this Snoopy. Yeah, so I think I try to explain you most of the important parts in the introduction. I'm not sure we have been taking a lot of time, so shall we take a coffee break or shall we continue? What do you think? Okay, shall we start or?
You're welcome to start, Solomon. We are already here. Thank you.
Yeah, okay. Thank you so much. Sorry, there is a lots of things that we have already prepared. Unfortunately, we don't have the time schedule. So we have already discussed with Professor Francesco that we might have additional high performance masterclass in the future. But today, Professor Onime will continue with the parallelizing parallelizing serial to parallel OpenMP. The floor is for you, Clement.
Okay, thank you, Dr. Solomon. Yeah, there is generally a lot to say about HPC. Okay, so let me share my screen. Okay, we'll just briefly talk about how you can parallelize existing code. We are going to be talking about a technology known as OpenMP. And I hope in sort of a quarter of an hour, I can give you a brief introduction to this. Hopefully next time we'll do some hands-on demo, even on your laptops. However, I believe if you downloaded our recommendations about the compiler, you will discover that implementing OpenMP yourself is not something that is very difficult. The first thing to understand is that OpenMP is not a computer language. It's not something similar to Fortran. It's not C or C++. It's basically known as an open specification for multiprocessing. And this is why the acronym OpenMP. And it's essentially an API. So it's just a programming interface. And this means it can be used on very many platforms, on Windows, on Linux, on a Macintosh, regardless of your particular device. And because it doesn't have, it's not a programming language, you can only have directives and library calls, as well as environmental variables. Okay. So the basic idea is given by this diagram. So we have an application arriving at a situation where it divides itself using a process known as fork into several different threads, okay, that are running different parts of the code or even running things in parallel. And then after they've all worked for a while, they come back together again and can become a single thread. Then the whole process can be repeated. So the region between when we divide and when we come back together is typically known as the parallel region. So the key idea is to say, okay, we can parallelize bits of our code to get huge benefits in speed. So it's very easy parallelization, and it hides complexities of thread programming. So the directives are instructions to the right compiler. So basically, when you put directives in your code, they are ignored by a compiler that does not understand those directives. So these tend to look like comments to other compilers. For example, the OpenMP sentinels are typically the directives that start or end OpenMP blocks. So in C or C++, this will be a hash pragma OpenMP. So once the right compiler meets this directive, it knows that it has to do some things in parallel. So it has to set up a parallelization environment, and this is for Fortran. Okay, so if you are using the GNU compilers, we have given directives, or we have given some hints about where you could get a free programming environment, the CodeBlocks IDE. You can, in principle, there are compilers there for Macintosh, for Windows and Linux. You can add this flag to the C compiler if you have the GNU compiler, -f OpenMP. This simply tells your C compiler that we are going to include OpenMP, or you should expect to include and interpret OpenMP directives in this file. Okay, so for Intel compilers, it's a different option, -OpenMP. If it's the Fortran compiler, it's IFC. Okay, so the flags for starting are these. The directives, this is what you put in your code. And then since it's mostly for parallelization, there's a lot of focus on loops. So you can trigger the fact that you are going into a loop. So most of the time, OpenMP tends to be used to wrap up loops that will have been run serially. Okay, and so these are some of the other directives that you can come across. For example, this is a C code, okay, and we define a single variable. Okay, so at the time this variable is defined, the code is running as a single thread. So that becomes like a shared memory space for all the variables. Once we hit this directive, then everything between this opening brace and closing brace will be done in parallel. Okay, so essentially it simply identifies himself using a thread number, and then he will perform some calculation based on the location here, based on his ID. Okay, and then once the block terminates, you get a single process again, and you print out all done just by a single thread. So in the last example, we used a function called set number of threads. You can see here we say OMP set number of threads. So this means this application, once we hit this directive, will create 4 threads. So it's going to have 4 parallel threads or sessions running together. And so you can set that from your application, okay, or from the library. So you call the library within your application. You can also set environmental variables, okay, to determine the number of threads. It's always a zero-based system. So the first thread will be called thread 0, or it has an ID of 0. Okay, some of the common library functions are you can get the number of threads, so you can find out the global number of threads. You can get the ID of the current thread okay, you can actually test if this section of the code is being run in parallel, okay? And you can return the maximum possible threads as determined by the operating system. And so operating systems look at your processor, and based on that, they determine the number of threads. For example, if you have a 20-core processor, then you tend to have 40 threads. This is also based on things like hyperthreading, which I mentioned briefly in the previous class. So the maximum number of threads that are recommended for that platform is going to be 40 if you have a 20-core processor. Of course, you can set it to be much higher, but then you get a degradation in performance. Okay. So this is a more complex program that is simply going to print out the famous hello message that we find in many C books. Okay. So this is, we include the OpenMP header. And then this section is what is run in parallel. Okay, this section is run serially. It prints out number of threads along with the thread ID of each one. And then we're back to the sequential world and it returns 0. Okay, we can have the same example in Fortran. And so within your thread, you can also have private variables, or you will have variables that are global, so variables that are shared across the entire application. So one of the key benefits of OpenMP is the fact that it can significantly reduce the overhead of looping. So each time you have to do loops, like maybe perform some calculations using on matrices where you are using multiple levels of loops. For example, matrix/vector multiplication, you tend to have several levels of nested looping. You can easily ask OpenMP to parallelize that. Okay. And some of the techniques are that each thread can calculate a start region and an end region. So they only carry out a fraction of the thread. So here we have a loop that is going to go from I start to I end, but we calculate I start based on which thread we are. So you have a gap, okay, and this automatically splits the task into different number of threads, and we'll run that on your behalf in parallel. Okay, so this is a sequential program. So we are going to loop through 1,000 locations one by one. But if we have the OpenMP directive here, the loop, okay, will simply be converted to parallel. Okay, so if we're using 4 threads, it means each of the threads will automatically do 250 as opposed to run looping for 1,000. And this gives you a huge benefit, a 4-to-1 ratio in savings. So basically, when it divides, it sort of divides between threads until it arrives to the end. So even if the number of threads available doesn't completely match the loop values, it's sort of going to try and handle it smoothly. You can, in principle, also improve this by using chunks. So not just looping. So you also have your data blocks as sort of blocks 1, 2, and 3 are handled by one core. So this is a situation where we have 4 cores. So 4, 5, 6 are handled by the next core, 7, 8, 9 by the green core, and then we have 10, 11, 12 by the blue core. So this can go on until we get to the end of the loop. So this is when you specify that you want your loop to be scheduled with 3. Okay, you can also have dynamic, in which case it's sort of interweavals. So you have 1, 2, 3, 4. then 5, and so on and so forth. Okay, so at the end, what tends to happen is if one thread finishes earlier than the others, then the OpenMP library automatically causes that the thread that has finished to wait until the others get to the same end before continuing. If you want to avoid this, you can also specify a no wait clause for the loop directives, and that will sort of allow the thread to continue going on its own. I believe this is the default when you use the Fortran programming language. You can also have some other optimizations in OpenMP, something called reduction. Reduction tells how he should group variables together. So assuming you have a private variable that is private to just a loop, like if you're trying to sum up, okay, or add things together, you can always use reduction to aggregate all the individual sums from the individual loops together. So at the end of the construct, you get a single global variable that contains all the local copies of your. So we see an example here where the variable ZZ, although it was defined globally, we're told, OpenMP is told that that should be a private variable, and our reduction is going to be sum, okay? So essentially, ZZ becomes private, the sum gets added, and then when we finish, all the sums from the various threads are collected together, and you have your output in the sum variable. So this is just another example that is common practice, especially when you are looking for things like 1 million values. And this one is to calculate the area under a curve. Okay, so it's simply the equivalent of carrying out an integral. So the integral of this function, okay, and the final results we expect should be 1/4 of pi. So at the end of the day, if you carry out 1 million or more calculations, it will take a significant amount of time when you are looping over 1 million iterations. And so OpenMP can help you significantly reduce the amount of time that will be spent in performing this loop, because it splits into threads and then performs the computation using that. So you can also make your parallelism based on conditions. So we only go parallel if the available tasks are greater than 1,000. So if not, we sort of treat everything serially. Maybe in this situation, the processor has enough cores to handle things serially, so you don't have to do anything more. Okay, so these are just some watch-outs, especially with performance with respect to OpenMP. The thread overheads may not always be negligible, especially if you are trying to create a huge number of threads. OpenMP is not the same thing as programming GPUs, but it's really a quick strategy for taking an existing application, either C or Fortran, and converting it to a parallel application. So it usually can give you significant speed benefits, especially if you have to do a lot of looping. It will only work for shared memory systems, so you can only use it within the confines of one computer. Okay, thank you very much. Dr. Solomon, are we there?
Yeah, thank you so much. Yeah, okay. I think we have around 10 minutes now. If you have any questions, you can ask. But there is many things that we would like to show you, but the time is not enough that much. So we have to keep the schedule time, and probably next time we will have another high performance machine training, which we will announce it soon, and then try to provide the rest of the things what we have already. And Francesco?
Thank you very much, Solomon and Clement. It was really an enjoyable masterclass. And as you say, Solomon, I think we are all looking forward to have a follow-up masterclass in the new year. Yeah, so we will. This is a topic that attracted lots of attention, and we will keep pushing it. Yeah. So thank you very much for both of you for this very nice introduction. And we are looking forward to keep working with both of you in our cluster of research excellence. So thank you very much to all the online participants. I also thank the participants here in our venue in Stellenbosch. And I'm sure there will be lots of participants at many other venues. So thank you to all of them. And we will soon advertise the next masterclass, which will happen, I think, mid-January, if I remember correctly. Yeah. So thank you very much, everyone. Have a good afternoon. Thank you. Thank you very much.
Thank you, Francesco. It was also a pleasure meeting you.